All right, let's chat implicit, and I'm probably going to make a horrible mistake in trying to answer that question we had at the very end of class about horizontal and vertical tangents by doing it with this problem. I think it's going to be a bad idea. I'm still going to do it because that's me, trying out things for the funsies of it. So we have our last example from the notes, which we did not get to on Monday. So I did promise to make a video. Figured we'd just start there. So part A, this is what I typically do on the exam. I give you a function. I say, show me what the answer is. So I've actually told you what you should end up with. That should make things easier, but occasionally makes things harder. So we are going to take the derivative with respect to x of both sides of our implicitly defined function. In order to do that, we have to recognize that we have not one, but two product rules coming up, right? We handle problems just this gnarly today in class. So we go, okay, fine. First product rule, we're going to get y squared plus 2y dy dx times x, right? I'm just writing these in that same structure we're used to seeing so that we can recognize everything happening there. I did not write that derivative of x, which is 1 out in front, but I could have if I really wanted to hold hands, right? So 1y squared, derivative of the first function times the second, plus the derivative of the second function times the first. And we're going to do the same thing with the second term. I'm going to go ahead and lump the negative in with the x cubed, make that my function, my first function, just because then I don't have as much bookkeeping. I don't have to have big old parentheses with that negative sign out in front. So if I keep going, now I have derivative of the first times my second plus the derivative of my second times my first. And again, I'm being a little extra here, but oops, that is not the first. I did the derivative because I was talking. There we go. And this is all equal to 0. And I'll go ahead and come in here and highlight those pieces that we're used to seeing so we can see them again, all pretty. All right, if we're going to clean everything up, of course, if we're just trying to show this, I have enough personally to show it, but of course, this doesn't feel like enough for a lot of people, so I'm going to go ahead and clean everything up. For every term, I'm just going to put any of those factors of that term in front of the dy dx just to kind of organize things. And I, of course, like things alphabetically, so when I multiply that x in here using that commutative property, I'm going to write it as 2xy. This is not required. It's just cute. Minus 3x squared y, that's already alphabetical. And then minus x cubed dy dx. This is all equal to 0. So just a little bit of housekeeping. You probably did this as you were multiplying, but I'm moving a little slow just in case we need to. So now I want to isolate those dy dx's, and since this is a show problem, I'm going to make sure it's really clear every single step. Even though I might be able to do this in my head, I'm going to make sure everyone sees what's happening, right? The show is sort of like make your thinking really visible, even if you can do it in your head, right? And then I'm going to go ahead, because I am a little bit impatient and definitely running out of room, I will factor that dy dx out of those remaining two terms in this line. I'll go ahead and write these in the order we see in our answer. And we'll come into our final step, which is to divide out that 2xy minus x cubed and 2xy minus x cubed. And so we can see this thing looking exactly like what we were supposed to get. So we get to pat ourselves on the back and be done with this problem. Now the follow-up to this, part B, says find all points on the curve whose x-coordinate is 1 and write an equation for the tangent line for these points. Now this is very similar to what you're going to see on Friday's quiz. Part 1 is just going to be a basic implicit, kind of like our A, and part 2, our second question is going to be finding the equation for an implicitly defined line. So it's our first real time of finding a tangent line in this class, officially. On a quiz, that is. We've found a lot of equations for tangent lines. All right, so we want the tangent line. We know we're probably going to need this. Point slope form. We have to be really careful here. A lot of students, not a lot, but some students will put in this entire equation as dy dx. And while that's not incorrect, that is not a linear function, right? We need a number here for our slope. So what we need to do is plug in x's and y's to get out that numeric value of the slope when x is equal to 1. Unfortunately, this derivative, this dy dx, needs an x and a y. So we need to go figure out what our y is. So we go, oh crap. Well, we do have a way to get our y. We got to go back to the original function, our OG function, and we're going to go ahead and plug in our x of 1. So this would be 1 times y squared minus 1 times y is equal to 6. Hopefully we recognize whenever we end up with something with a squared term, right, a squared variable, our solution, our way to solve this is typically going to involve setting aside equal to 0 and hopefully factoring. So y squared minus y, I'm going to subtract that 6 from both sides. Get me to that. And then what is the magical, completely unrealistic thing? In most first semester calculus classes, this factors. And I had an old student, Stan, who refused to ever factor anything and always used the quadratic formula, which is a choice and it will always work. So anyways, we end up here and we get two possible y values. We get a y of -2 and a y of -3. So it's really easy to get distracted. We still have a lot to do here, right? We need to figure out what the slope is still. And now we just have all the stuff we need to plug into that formula that we found, that derivative. So let's just go ahead and do the first one for, I'm going to go ahead and label it dy dx for our point 1 comma -2. If we plug in 1 comma -2, we're going to get 3. I'm going to be really slow about it. I'm regretting my choices. I'm not going to be slow about it. I can't do it. Can't, guys. I can't. All right. So we end up with 3 times 1 squared times a -2. That's -6 minus a -2 squared, which is a 4. Right? -2 would be a +4, but we're subtracting it. 2 times 1 times a -2. That's a -4 minus 1. So it looks like, oof, we're going to have to check my work. We get a -10 over -5, a +2 for our slope. So already I could write out number 1, line number 1, y plus 2, ooh, that 2 looks ugly, is equal to 2x minus 1, that quantity. All right, so that was our first one. Let's go ahead and find our second point because there were 2 points with x is equal to 1. So our dy dx at 1, oh, I said -3, +3. See, I'm always busy thinking about what I'm going to say next and don't make those silly mistakes. Okay, so again, we're coming back to this derivative function. We're plugging in. We still have 3 times 1. Sorry, I'm processing. 3 times 1 times another 3, that's 9. Minus 9. Oh. Well, let's make sure this isn't a 0, because if it is a 0, we have an x is equal to line. We have a vertical line. But let's double check. We end up with 2 times 3, which is 6, minus 1. So this is 0 over 5, which is just 0. So here, our second line, hopefully we are correct, or I am correct. Y minus 3 is equal to 0, x minus 1. You can leave it like that, but this is just the line y is equal to 3. So because I am a glutton for punishment, I am, you know it, gonna pull up Desmos to see if I'm right. And when I'm wrong, the typical thing I do is cry. I'll have to figure it out live on camera, but that's the way I like to do things, is just by the seat of my pants. It's hubris, I think, to never try problems before you start doing them. All right, so here's our lovely implicitly defined function. We were talking about x is equal to 1, so I guess I can zoom in a little bit. Yes. All right, so we got these points out, 1, 3. Uh-oh. Was it in 1, it's already bad. It's already bad. How? X is equal to 1. Plugged in 1. That's all good. That is a -3 and a did I type in the equation wrong? Y'all. Yeah, I did. See? Feel better about my life. Whew, there they are. There are my points on my graph. Whew, I didn't even see it. Okay, so now if we wanted to double check, here's how I would do that. I'm going to go ahead and type in the actual lines that we found, right? So I'm going to go ahead. We found at 1, -2, this baby here had the slope of 2, right? So this was y minus plus 2 is equal to 2x minus 1. And we look, and that looks pretty legit. That looks, and right, what I did in today's thing is I went here and I actually made this little dash line so we could see it a little bit better. That looks beautiful. That looks very tangent to that curve. I'll make it green so it matches my point. And now the other one, this is the one where we got a slope out of 0. That seems pretty legit. We are getting that turning point there, that local minimum. So we could just type in, this is y is equal to 3 is what we ended up finding. And again, I'll just go ahead and make that dashed. And I can't get to the blue, but we'll just change this one to black so they match. Cute. All right, so yeah, that all worked out. I did not make any mistakes. Yay. For once. For once. All right, and now here's where I'm going to regret my life choices. We're going to go ahead and use this again, this same problem. I'm going to grab both the original and its solution here. It's dy dx, not solution, but its derivative. And we're going to talk about horizontal versus vertical tangents. Because we did see, right, in that Desmos I just pulled up, there was a nice horizontal tangent here at 1, 3. So let's see how we might find those. So as we discussed in class today, horizontal tangents are when our slope is equal to 0. Slope is equal to 0 if our dy dx is equal to 0, which means our numerator is equal to 0. So if I want to find my horizontal tangent, those points where that happens, I am going to go ahead and type or set 3x squared y minus y squared equal to 0. Now, this is why I've chosen a horrible thing. This is not going to be easy, but I like a challenge. So we get y and 3x squared minus y, because we know we need to factor, because there's a bunch of stuff going on there. So we at least have one easy solution. Y is equal to 0. We also get out this thing, which is 3x squared minus y is equal to 0, which we could write as 3x squared is equal to y. Okay. So unfortunately, this only gives us a single coordinate of our point for our implicitly defined function. No matter what, even if this had been a less disgusting question or particularly function, not function, but relation, we would still have to do this work. So what we're going to do now is we need to go find our x's based on these y's. So the y should be straightforward, hopefully. We plug in 0 and we get x times 0 minus 0x is equal to 6. We get 0 is equal to 6. So it turns out easy is maybe not the best word to use. 0 doesn't have a solution. There is no point at 0. Let's go verify on our graph. Yep, it looks like it's 0. We're getting an asymptote, right? Bad things are happening at 0. Who knew? Okay, so this is all out. Let's go look at this one then. We can do this. This is harder, right? Because this doesn't say y is equal to 2. It says y is equal to 3x squared. So we're still going to be able to do this. We're going to go ahead and everywhere we see a y, we're going to replace it with 3x squared, because then we'll at least give ourselves a equation that only has a single variable instead of 2 variables, right? Right now we're solving a system, a nonlinear system of equations. So this is x times 3x squared, that's my y, right? Squared, minus x cubed times this 3x squared is equal to 6. So all I have done is rewrite this thing with what we said y must be equal to. With a little bit of math in here, we get 9x to the 5th, right? This square applies to both my 3 and my x squared. That would give me 9x to the 4th times x. Minus, I am going to cry. Oh, that's not a 9, thank God. I was like, this isn't going to work, and I'm all wrong, and I don't know what, and I've talked so confidently. I'm good. Yeah, so we end up with this. 9x to the 5th minus 3x to the 5th is equal to 6. That means we have 6x to the 5th is equal to 6. and my small panic attack aside, we get x to the 5th is equal to 1, which only happens when x is equal to 1. So there is a single horizontal tangent, and it occurs at x is equal to 1. Now, of course, we still need to go back and plug this in to get the other part of our point. If x is equal to 1, y is equal to 3. So we got out that we have a horizontal tangent at 1, 3, and only one of them. This matches what we saw in our graph, right? We weren't guaranteed that there wasn't another horizontal tangent, so all this work was lovely and needed, but we can see, yep, there it is at 1, 3, my horizontal tangent. So I'm going to regret it, but let's go ahead and find our vertical tangent. So let me duplicate this screen. I think I can. I think there used to be a thing. Aha, yes, I can. Let's copy her over, and then let's erase and redo this for vertical. Okay, so for a vertical tangent, that happens when our slope is undefined. Okay, and that was the other thing, by the way, when Miss Gina's worksheet, she asked for the equation of the tangent line. So she actually went further than this and said, well, if it is horizontal, horizontal lines have a equation of y is equal to, right? So that's where she was getting those x is equal to, y is equal to, was by figuring out the other coordinate and then making a flat horizontal line with y is equal to. All right, so vertical tangent. Sorry, that was a random aside. I just realized her thing. Both Allie and I had questions. She was like, what are you doing here, woman? All right, vertical tangent. All right, vertical tangent line is when our slope is undefined, right? We have the vertical line, which has a slope that is undefined, which is what happens when we divide by 0. So we're going to do the same thing we did before, but with our denominator set equal to 0. Again, I'm going to factor because I don't see any other way out of this fresh hell. And then I'm going to set my two factors equal to 0. So we have it x is equal to 0 and 2y minus, I'll be slow about it, is equal to x. So x squared is equal to 2y. Okay. All right. Or I guess maybe we'll be good about it and do y is equal to x squared over 2. I was debating how I was going to solve that. So we already know x is equal to 0 is going to be a problem because when we looked at it back here and we tried y is equal to 0, oh, we don't know about x. Y is equal to 0 was a problem child. Ooh, let's see. All right, so if we plug in x is equal to 0, we get the same thing. There's not actually any points that we get for x is equal to 0. Part of me wants, sorry, I'm not trying to pull up my email. I'm trying to pull up my Desmos because now my brain is slowly ticking away. I guess you're right. Okay, sorry. This is me really thinking about it. In order for that to be 0, it needs to approach the same thing from both sides. I was thinking about this y equals. It does look like we're starting to get a vertical tangent, sort of that horizontal asymptote, but we're not actually ever getting there. And, just like over here, right? We never get to that horizontal tangent. We have these slopes that are approaching 0, but they're never quite there. But additionally, on this side over here, as we move towards that, towards 0 from the right-hand side, it doesn't match what's happening as we move towards 0 from the right-hand side. So my brain was processing all that very slowly. So again, this gives us nothing. So we're going to have to do that same substitution game with this other one. Let's try it. So we have x times x squared over 2, and then an x cubed times x squared over 2, all with a 6. So we get, this is another x to the 5th over 4 minus x to the 5th over 2 is equal to 6. Your choice how you wanted to handle this at this point. You could just multiply everything through by 4 to say f. I don't want to deal with any fractions. I'm going to continue on with it as is because 1/4 minus 1/2 is something, oops, I can do as long as I'm not talking during it. And then we can multiply both sides. I guess I could have done the negative. It's too late now. I'll do it now. Okay, so we get x is equal to the 5th root of negative 24. And 5th root of negative 24 is allowed. Let's go see what the heck happens when we put this into, to Desmos. Get rid of these things. We don't need them anymore. I don't even know how to do, I'm just going to do 24 to the 1/5 because I don't know how to make a 5th root show up. So that is 1.888 blah, 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 blah. For x, I don't feel good about that. 1.8 is like right here. Oh, but there's another 1.8. No, that's still not good. Oh, it was a negative 24. Oof, you guys get to hear me talk all this stuff. That feels good. That feels like right there. That feels like a, ooh, yeah. Oh, yeah. That feels good. I feel good about this. Let's keep going. Let's keep going, because this lovely thing right here would be our horizontal tangent, right? Let's do this. Okay. So again, we still need the rest of this point. So we would need to plug back in to this thing. So our y would be equal to whatever the heck, negative 24 to the 1/5 times, or squared. So whatever that is. I'm just plugging this ish into there. So I'm going to go ahead and put that beautiful point on my graph. Oh, I'm excited about it. No one else is excited but me. All right, so that was already my x. Let's throw in my y. I'll make this a point. This was negative 24 to the 2/5, all divided by 2, I think. Ooh, I don't know about that negative and where it is. That negative needed to be inside this so that it got squared and turned positive. Oh, you want me to have actual parentheses on the outside? I get it. I understand. There you go. There's that point where we have our horizontal tangent. And if we wanted to write out the equation for that horizontal tangent, that would just be x is equal to, because horizontal line, I'm sorry, I keep saying horizontal, vertical tangent. Vertical lines are always at x is equal to. So x is equal to negative, oops, let's do this, negative 24 to the, not x factorial, to the 1/5. You can see that. Let me go ahead and edit it so she's a dashed line so we can really see it. Yeah, right up against there. There's that beautiful vertical tangent. So those two questions were much harder than anticipated in terms of like having to solve this nonlinear question that resulted from the only way I was able to get out a solution. But if you could follow what I was doing here, I am confident that you would be able to do the questions that you might see in Delta Math in terms of finding those points where your implicitly defined function has a vertical or horizontal tangent.